I have a problem here involving the polytropic process of helium gas in a piston cylinder system where initially the pressure of helium is 300 kilopascal and its temperature is given as 180 K and the mass of the helium is 0.5 kilogram. Notice that I'm not using any subscript for mass because it's a closed system, so mass is constant no matter what happens in terms of energy transfer to the helium gas. Heat is added constantly to helium, and we know that the process follows the relation between pressure and volume so that it is a polytropic process, and we're assuming that the polytropic exponent is 1.5 in this case. So basically we can write this equation that at any state p times v to the 1.5 is a constant. We are trying to determine the boundary work involved in this process while heat is being added, and we don't know whether the gas will expand or contract. The reason is that because it's a polytropic process, this is not a piston that is freely moving. It means that there is some restriction on the move of piston so that it follows this equation instead of being a constant pressure process. Constant pressure process is a special polytropic process where the exponent is equal to 0. In this case, it is not 0. So, to solve this problem, we can start by determining initial volume of the gas in the cylinder. The end condition given is that after heat added, after some time, the given condition is that the final pressure will be equal to 250 kilopascals. All right, so one more time, reviewing the problem statement, we have helium gas at 300 kilopascals and 180 Kelvin in a piston cylinder system. The mass of the gas is 0.5 kilograms and the polytropic exponent is 1.5. The process continues until the final pressure is equal to 250 kilopascals, and the question is, what is the amount of boundary work involved in this process? So we can start by determining the initial volume of the gas in the cylinder. So this is an ideal gas process, so P1 V1 is equal to MR T1. This is the ideal gas equation of state. You can write it for ideal gas at any state. We need to read the value of gas constant for helium from table A1, and the value is 2.0769 and the unit is kilojoules per kilogram per Kelvin. Now we can determine the initial volume as MR T1 divided by P1, or 0.5 times 2.0769 times temperature divided by pressure, initial pressure, 300. That is equal to 0.623 cubic meters. This is the initial volume of helium gas in the cylinder. So we start with the general equation for boundary work of an ideal gas, or in general any gas, but we're talking about ideal gas right now. So the boundary work is equal to integral of P times dV from state 1 to state 2. Now we need to have a functional relation between pressure and volume to be able to calculate the integral. So we know it's given to us that this is a polytropic process with a polytropic exponent of 1.5, and we know the equation for the polytropic process is PV to the n is a constant. In this case, PV to 1.5 is a constant. Rearranging this equation will result in P is equal to CV to the negative 1.5. Now we can plug in this equation, which would result in integral of P, which is CV to the negative 1.5 times dV. The answer to this integral is, of course, C over negative 0.5 times V2 to the negative 0.5 minus V1 to the negative 0.5. With some operations, we can eliminate the need to calculating the value of C. Keep in mind that you can calculate C by plugging in initial condition P1, V1 into this equation and calculate the value of C and plug in here. Another method is to just do some operations and eliminate C, eliminate the need for calculating C. So I'm going to do that. So looking at this, that's equal to negative 2C actually. Negative 2C times. So what I'm going to do with this, these two terms is that I'm going to break it up to V2 to the power 1 times V2 to the power negative 1.5. I'm going to do the same to the second term, V1 negative 1.5. So looking at this, now one more operation. So negative 2C times V2 to negative 1.5 times V2 plus 2C times V1 to negative 1.5 times V1. I am going to separate these two parts. So looking at these and back to the equation governing a polytropic process, you can see that C times V to the negative 1.5 in this case is P2 and this one is P1. It means that I have negative 2 P2 V2 plus 2 P2 P1 V1, or switch places 2 times P1 V1 minus P2 V2. This is boundary work during this process. We just need to plug in some values. Now, looking at what's available to us, we see that we know P1, we know V1, P2 is also given, but we don't know V2. What we should do is use the polytropic process equation to find the unknown V2. So I'm going to write it for both states 1 and 2. Because it's constant, P1 V1 to 1.5 is constant, it doesn't matter what state I write it for. So these two are constant. The left hand side and right hand side are equal. So it means I can calculate V2 to the 1.5 as P1 V1 to the 1.5 divided by P2. Plug in values, 300 kilopascals, 0.623 to the 1.5 divided by the given final pressure, 250. The answer is 0.59, which means final volume is 1.5 root of 0.59, which is 0.703 meter cube. This is the final volume. Now, I'm going to use this equation for boundary work. Now that I know everything on the left-hand side of the equation, which is right-hand side of this new equation, I can calculate the boundary work. It's 2 times 300 times 0.623 minus 250 times 0.703. Boundary work, we calculate it as 22.3 kilojoules.